Hello, everyone, and welcome to this webinar today. So thanks for joining. My name is Jean-Philippe Gagnon, and I'm a field application engineer at Telops. And I'll act as chairman for this presentation here today. Like I said, I will be your host, and I just wanted to quickly get a few housekeeping things out of the way before we get into the main presentation from our presenter today. First, I want to let you all know that this webinar is recorded, and a link to a download or a link to download or view the recording will be sent to all attendees in a follow-up email after the webinar. We also encourage questions from the audience. So if you hear something during today's presentation that sparks some interest, or you would like to have more information on some aspect or things that were discussed during the presentation, please feel free to use the GoToWebinar question box. We will reserve a few minutes at the end of the presentation to answer as many questions as we can, but in case that we don't get through all of the questions, we will answer them offline in the follow-up email. All right, with that intro out of the way, I would like to ask a little about our audience today using this poll question that we'll bring up in just a few seconds. So it's just a simple question. Here it is. You should all be able to see it. So basically, how would you rate your knowledge of hyperspectral imaging technology? So there are 4 choices. So you have no direct experience, but you are interested in the technology. No direct experience, but have considered the technology before. So you're aware of it, that it exists and a little bit how it works and the application you're able to do with this technology. Choice C, you have direct experience with collecting and processing hyperspectral infrared data. And the last one, D, is you are a thermal hyperspectral imaging expert. I'll just give a few more seconds to give a chance to everyone. Right, I think we have most of the people have voted, so I'll close the question poll and share the result with you. All right, here are the results. So most of you, I think, in the first 3 categories. So I think the results of this poll question helps us a little bit assess the level of understanding or the level of knowledge of our audience. So that will be good. It helps me. Also, it tells me that I should maybe explain a little bit how the technology works, and that's exactly what I will of the webinar. All right, let's close the webinar and dive into the main part of the presentation. Share my screen. Okay. So yeah, this presentation here today, we are fortunate enough to have with us Gilles Parent from the LEMTA research facility here, who will talk about combustion, characterization of flames with Telops Hyper-Cam. But first, let me just go through a little bit of what Telops is, our products that we offer. Then I will focus on hyperspectral infrared imaging to let you know how it works, what kind of instrument it is, how it performs, such that you'll be prepared to understand or follow Gilles Parent's presentation. Like I said, we'll have a short Q&A session at the end of the presentation. All right, so Telops started back in 2000. Right from the get-go, Telops engineers and scientists really focused on really R&D projects based out of infrared technology, quickly developing the hyperspectral systems based on infrared detectors and hyperspectral or interferometers. After that, we moved into making our own infrared cameras, all kinds of infrared cameras. But yeah, and quite recently, Telops was purchased by the Photonis, now called Exosens Group. So we're part of a much larger family now, which is nice. So the kind of products that we offer, if some of you don't know already, our lines of broadband and multispectral infrared cameras are the fastest on the market. We have multispectral cameras that are able to time-resolved multi-channel, to provide time-resolved multi-channel imaging, up to 8 filters. So provides you a good spectral information at a very fast frame rate. Also have high dynamic range cameras that allow you to, continuously measure scenes that are very high temperatures, up to 2,500 degrees Celsius. On the right, we have our line of high performance fast cameras. So like I said, these are the fastest infrared cameras on the market today, up to 120,000 frames per second. In reduced window mode. So these are great to attack, very fast events. And also our entry-level cameras, which the customer has the benefits of using Telops cameras with the proprietary permanent calibration to attack their application. Moving on to our line of infrared hyperspectral cameras. Of course, we have our flagship product, which is the Hyper-Cam, which was designed back in 2005. So we've been running with it since then. But a few years ago, we started to work on it to reduce the size, weight, and power of the unit, making it a much more a smaller unit, capable of being integrated and used in different applications, but keeping the same concept as the original Hyper-Cam. So very high sensitivity, very high spatial and spectral resolution. So the evolution of the Hyper-Cam moved into or ended up with 2 different products. So the Hyper-Cam Airborne Mini, which is the airborne hyperspectral system, and a ground-based version, the Hyper-Cam Mini XLW. Some of the applications now that these cameras are usually used in. First is ballistics, to study muzzle flashes or hot gases being ejected from either cannons or other arms for the military. Combustion analysis. So you see here a picture of the inside of a diesel engine, I think, where the gas is being introduced and then burned. So combustion research is an important application for very fast, and as you can see, these are very high, very fast event, very high energy events. So they need very fast cameras to keep up with the nature of the application. Experimental mechanics, also studying the characterization or studying the different properties of different materials. Again, some of these challenges or some of these applications require very fast thermal imaging. Gas detection, of course, is one very important applications for our line of hyperspectral cameras. Being able to detect and measure gaseous components in all kinds of situations is a great advantage, both from the military point of view and also from the environmental and oil and gas industry. where they're trying to reduce their overall emissions, greenhouse gases emissions, let's say. Again, hyperspectral cameras can be very beneficial in the field of mineral identification, where you can identify different mineral signatures on a mine face wall, like the example that I shown here on the bottom left. Infrared signature, of course, in the military, being able to recognize and study signatures of different engines is important. And most recently, additive manufacturing has become more and more used in the industry. So our cameras are able to measure or different properties during the additive manufacturing process, such as melt pool temperature determination and studying sparks that are ejected from the process to try to minimize those. Those are important aspects. And of course, non-destructive testing, being able to locate defects on a piece of material without having the need to really break it or destroy it is very advantageous. All right, let me now focus on hyperspectral imaging. Like I said, this will give you, I think, a good basis to really Mr. Perrin's presentation at the end. So there how I made a little sketch of how the instrument is working on the inside. So at the heart of the hyperspectral camera is what we call an interferometer. So this is a Michelson type interferometer. So on the left you have the scene. So the photons from the scene enters the instrument and encounters what we call a beam splitter. And this is the little green element at the center of the red rays or red light or straight lines. So this piece of equipment has the property of being of letting 50% of the light go through and 50% of the light bounces right back. At the end of the two arms we have, or two paths of the interferometer, we have mirrors, and these reflects the light back onto the infrared detector. So the concept of the instrument is all based on interference of light waves. So the light waves will interfere either constructively or destructively. If you remember your basic light or optics classes in school. So that's what the infrared detector measures. It's the interference or the intensity of the light waves that have been in constructive or destructive interference. So by moving one of the mirrors, we generate this interference pattern that we call the interferogram. And once we have recorded this interferogram, we apply a mathematical function to it, which is called the Fourier transform. And this transforms the interferogram into a spectrum. So the instrument, the end product is a spectrum, but the raw data is called the interferogram. So the interferogram, you can think of it as a series of infrared images, all acquired at different position of that moving mirror. So the instrument in all will provide what we call the data cube, which is a series of images acquired at different wave numbers or different wavelengths. But the raw data is a series of images acquired at different time or different position of that moving mirror. So the overall making or collecting one data cube is pretty slow. That meaning it can take seconds or minutes in some cases. But on the inside, the instrument is recording a series of images at very high frequency, very high frame rate. So those images are part of the interferogram. So that's an important concept if you want to follow through Mr. Perrin's presentation later on. So the raw data consists of a series of images acquired at very high frequency, and we apply Fourier transform on top of that to create the spectrum data cube. A couple of examples to illustrate the kind of data that is being produced. Like I said, The end product of the camera is what we call the data cube. So a series of images acquired, or a series of images at different wave numbers or wavelengths, depending on how you want to look at it. But if you click on a single pixel, you have the corresponding spectrum. Like here on the left, we have a mine face that we've imaged. So on the top, you have the infrared imagery, and on the bottom, you have the corresponding visible imagery. And if I click on here, I selected 2 different pixels, and you can see the kind of data that it produces. It's very different. It's based on the material that is that a pixel corresponds to. So different materials have very different signatures, and that's exactly what we see here. And on the right-hand side, we're looking at the aircraft on the runway. Same concept. We have a data cube. So if I select 3 different pixels at 3 different areas of the image, I'll be able to always see the corresponding spectra. So they look very different because we're looking at very different things. So the one on the left is the hot gases being expelled from the jet engines. And you can see a lot of emission spectral lines from the different gases within the hot gas plume. If I click on the fuselage of the aircraft on the top, you can see it's pretty dark on the imagery, meaning it's pretty cold. So that is very reflective. So what we see here is the reflections from the sky overhead and the atmosphere. So we see a lot of emission features from the atmosphere. And on the right-hand side, we see the pavement spectrum from the pavement. Again, it looks very different. That's because the pavement is made up of quartz, and we see the signature of quartz within the pavement itself. So these data cubes, the spectral data cubes contain a lot of information. They're very rich in information, so we can extract a lot of knowledge or information out of those. And it's exactly what we see in the next presentation. Moving on, so that ends my part of the presentation. So let me introduce our main presenter today. Mr. Gilles Parent is a professor at Laboratoire Énergie and Mécanique Théorique et Appliquée, or LEMTA, at the Université de Lorraine in France. He has been working for more than 20 years on thermal radiation and radiative heat transfer in very different fields. 10 years ago, he joined a team dedicated to fire sciences, still focusing his research on topics related to radiation. He has been using Fourier transform spectrometers, thermal infrared cameras, including multispectral cameras, and more recently, hyperspectral cameras. On that note, I'd like to pass the controls to Gilles Parent for his presentation.
So today I'm gonna present you some work done with the Telops Hyper-Cam to characterize the radiation emitted by flames. So because they are non-contact and therefore non-intrusive, optical techniques are among the most convenient and reliable techniques for characterizing flame. The laser-induced fluorescence, coherent anti-Stokes Raman spectroscopy, and tunable laser diode absorption spectroscopy are active techniques. That is, they require an external source of light. Example given, a laser to work. In contrast, emission spectroscopy is a passive technique. That is, it doesn't need any external source of light. However, the signal which is measured is integrated along a line of sight. Okay, that is, if the instrument look along this direction, okay, the radiation measured by the instrument is the integration of all the intensity, the radiation along this direction from -infinity to the instrument. So it includes the background radiation, which is attenuated by the absorption of the flame, and attenuated by the atmosphere layer, which is after the flame. And it includes also the radiation emitted by the flame, attenuated by the atmosphere, plus the own emission by the atmosphere. In this work, the Telops Hyper-Cam has been used. This instrument can reach up to 320 by 256 pixels, and its spectral range is 1,800 up to 6,500 centimeter minus. And this range corresponds to the mid-wave infrared. And the maximal spectral resolution of this instrument is 0.25 centimeter minus 1 resolution, which is a quite very good resolution. As briefly explained by Jean-Philippe, the Hyper-Cam camera is basically a Fourier transform infrared spectrometer, except that the usual single element sensor of Fourier transform spectrometer is replaced by a focal plane array sensor. So the result is that we obtain an interferogram for each pixel of the sensor. And once the Fourier transform of these interferograms have been done, we obtain one spectrum for each pixel of the sensor. The Hyper-Cam is calibrated at the factory for high wave number, which are quite insensitive to the thermal background due to the Planck's law. And for the low wave number, for which the radiation emitted by the background is non-negligible, it is necessary for the user to perform a calibration periodically. So the instrument is equipped by two black bodies, a cold black body at a temperature usually 20 degrees, and a hot black body at a temperature near 100 Celsius. And the entire calibration procedure is handled by a dedicated Telops software, which is named We Will Calibrate. So this instrument was used to characterize a V-shaped premixed hydrogen flame. And this flame produces only H2O because the only combustion product of hydrogen is water, that is H2. So this is a simple case that we wanted to consider as a first study because it is very simple. Okay, and we have shown in previous study that the temperature and the H2 concentration in the flame are rather constant along the flame thickness. And just to explain you, this flame is quite particular. That is, in this part there is a square vein, okay, in which the premixed air hydrogen is coming, that is fresh air, the fresh gases, okay, and the flame is anchored by this rod, okay. That is, the burning gases are contained in this triangular area, which is just above the rod. If I show you the video, maybe you'll see better. Okay, so the fresh gas are here, and the combustion gas are just in this very narrow V-shaped area, just here. In this picture, just a photo of the hyper camera, the burner on the rod. Just to explain, the measurements were done with the flame. That is the direction along which the Hyper-Cam look at is parallel to the rod. Okay, that is not like in this figure, but it was along this direction. So in this image, what we see is what would seen by a usual infrared camera. So what we see is this part that contains the hot gases, the combustion gases, in this V-shaped area. But the hyperspectral camera, it produces not only intensity, not just infrared images, but for every pixel of the image, we have an interferogram, as we see in this figure. So this figure, it represents the interferogram at this point here, at the position of which is 32 along the horizontal direction, on 39 along the vertical direction. So this is the interferogram, that is the raw data obtained by the instrument. Okay, and it is very typical of an interferogram with a central burst here. And we can see the baseline here is very flat. It is a very good quality of interferogram. This interferogram, if we do the Fourier transform of it, we obtain the spectrum. So this is the spectrum corresponding to the emission of the flame at this position. So now what we want to do is just to inverse the spectra in order to obtain some quantitative information about the flame. That is, what is its temperature, what are the species molar fraction, H2O, CO2, and so on. So the direct model, which is used for this inversion procedure, is a very simple model, okay, a two homogeneous isothermal layer. This layer here is a hot layer. It corresponds to the emission by the flame. We suppose that its thickness is 100 millimeter, and it is characterized by its temperature T hot, the molar fraction of H2O, H2 hot, the molar fraction of CO2, CO2 hot, which correspond to the CO2 which is naturally present in the atmosphere. And this cold layer is just the atmospheric layer, that is the air which is present between the flame and the instrument. And the thickness of this layer was 325 meters. So this layer is characterized by its temperature, another H2 molar fraction, and the same molar fraction from CO2 here than here, because for this flame there is no production of CO2 by the combustion. That is, the concentration of CO2 in the flame is exactly the same than the molar fraction of CO2 inside the atmosphere. So we have 5 parameters to determine: one temperature here, one temperature here, 2 molar fraction here, and 1 molar fraction here. Different techniques can be used to perform this inversion, and we have chosen the particle swarm optimization, PSO. And regarding the gas spectral model, we use the L distribution method, because this method is usable for very narrow spectral bands, and not every gas spectral model are capable of. It is very accurate because its accuracy is usually better than 1% vs the line-by-line reference model, which is the best one which is available, but it is faster than the line-by-line. And just to give you an order of idea, when parallelized and run on 40 cores, you can calculate up to 2,400 spectra per second. And it is very important to be very quick if you want to use the inversion code. And just to point out that this inversion has been made on the full spectral range. On this full spectral range contained 16,800 wave numbers, which is a very high number of wave numbers. So this is an example of this inversion. In this figure, what you see is the experimental spectrum in blue and the numerical spectrum in red. And as can be seen, there is a very good agreement between these two spectra. And the root mean square error is about 0.05 watt per square meter teradian centimeter minus 1. And the 0.05 is just 1/10 of this distance here. Okay. In this figure, there is a close-up just to show you how good the quality of this adjustment between the experimental spectrum and numerical spectrum. Just what I can show you is just that it is the same for almost every part of the spectrum. So yes. So this is the full spectrum, and what I can do is just to close up. Sorry. Okay. Sorry. Etc., etc., etc. So there is a very, very good agreement between the numerical spectrum and the numerical one. Just another part here. Okay. Okay. So let's go back to the presentation. The flame temperature that have been identified by the inverse method. So yes, the flame temperature is 1,270 K, and that can be compared to the adiabatic flame temperature that was determined to be 1,255 K. And the H2O molar fraction of the hot layer was identified to be 0.13, and the H2O molar fraction due to the combustion, that is what is contained in the flame minus what is naturally present in the atmosphere, is 0.113. That can be compared to what is predicted by a stoichiometric combustion that gives a molar fraction equal to 0.095. In this slide, what I present is a sensitivity of the signal, that is the intensity, versus the different parameters to be identified. So in green is what is the effect of changing the molar fraction of the H2O in the cold layer. So what you will see is that when we increase the molar fraction in the cold layer, the effect is just to increase the absorption. So the effect is just localized in this spectral range, which is specific to the absorption by H2. If you increase the molar fraction of H2O in the hot layer, that is in the flame, what you obtain is just an increase of the intensity emitted by the flame. And what is seen is that increasing this molar fraction by 2%, the result is an increase of 2% of the intensity. And if you increase the temperature, the effect is shown here, the blue curve. So what you see is just increasing by 2% the temperature has a big effect. That is, the average effect is around 10%. And this high sensitivity is due to the nonlinear behavior of the Planck function. We can see also that the effect is larger for the large wave number compared to what is seen for the low wave number, and it is due to the shift of the Planck function, that is what is corresponding to the Wien's law. In this figure, what is shown is the cost function. The cost function is the square average difference between the experimental spectrum and the numerical spectrum. So the best agreement is obtained when this cost function is minimum. And what can be seen in this figure is that in the entire parameter space, there is just one minimum, which is localized here, that is near the temperature equal to 1275 K on a molar fraction near 0.1. The same can be done for every pixel of the Hyper-Cam instrument to obtain temperature maps on H2O molar fraction. So what can be seen is that the temperature is rather constant in the entire flame. And the H2O molar fraction is not as homogeneous. Next, we have made exactly the same, but considering not just hydrogen, that is pure H2O flame, but a mixed flame including H2 and CH4, that is methane. So this flame has the same quantity of hydrogen, but 10% of CH4 has been added. What can be seen in this figure is that there is an additional peak here compared to what was obtained without the methane. And this peak is very specific, and it is due to the carbon dioxide. The temperature that can be identified through the inversion procedure is 1380 K. It is a little bit hotter than what was obtained with the pure H2O flame. And also what you can see is that there is an increase of the CO2 molar fraction compared to the atmospheric molar fraction, which was just 400 ppm. Next one is it's now a pure methane flame spectrum. It is pure CH4. The flow rate is 206 liters per minute, and the equivalence ratio of the flame is 0.5. Now, what can be seen in this figure is a very strong peak due to the CO2, the emission by CO2. And this peak is strongly attenuated in its central part due to the absorption by the cold CO2, because inside the atmospheric layer between the flame and the instrument, there is the atmospheric CO2, and this CO2 strongly absorbs the radiation emitted by the flame in this part. When you look at the parameters that have been identified, The flame temperature is 1680 K. That can be compared to the adiabatic flame temperature, which is a little bit hotter, but there is some radiative losses that explain why the actual flame temperature is lower than the adiabatic flame temperature. And what is observed is also that the CO2 molar fraction is 6%, 6.3%, whereas the H2O molar fraction inside the flame is 12%. And this ratio between the CO2 and the H2O is in agreement with the stoichiometric combustion, because, as you know, CH4 gives 1 CO2 and 2 H2O. In this figure, I just wanted to show you what is the emission by CO2. That is, the CO2 emission is the red part. So the strong peak here, around 2,500 centimeter minus 1, and also a little bit here. And in blue, the emission by the H2. This figure on the top corresponds to what is emitted by the flame, that is without the absorption by the atmospheric layer. And in the bottom figure, we have the same, except now the spectrum includes the absorption. So this spectrum is what is observed by the hyperspectral camera, because we cannot remove the air between the flame and the instrument. Just here a close-up to show you again this strong attenuation of the radiation emitted by the CO2 once attenuated by the CO2 contained in the atmosphere. Now I wanted to show you ongoing work, which is some results that are very preliminary. And in this part, we changed the type of flames. Previously, it was a laminar flame, premixed, and now it is completely different, because when you consider pool fire, what you obtain is diffusion flames that are very turbulent. So in this study, what we have considered was different liquid, methanol, ethanol, heptane, diesel, that were placed in a 30 centimeter square tray. And now the spectral resolution that was used for this study was 4 centimeter minus 1. It is very important to say that since the flame is turbulent, the flame intensity is not constant. So there are some strong fluctuations here. And these fluctuations are added to the signal recorded by the hyperspectral camera. So it is very it's very annoying, because the Fourier transform spectroscopy is not intended for observing such scenes which are not static or quasi-static. And the effects of these fluctuations are not known clearly yet. But what we did is just to correct first this interferogram, just to obtain a constant baseline instead of such an interferogram with these fluctuations. So once the interferogram has been corrected, we obtain this interferogram, which is by far better. And next step, we can make the Fourier transform to get the spectrum. So this is the spectrum. In this figure, we find again the characteristic spectrum obtained by the emission of the CO2, the strong emission peak here, which is attenuated in its middle by the CO2 absorption in the atmosphere, and here the emission by the H2. And this spectrum corresponds to a methanol profile. On the methanol, it produces a flame which has almost no soot. It is almost transparent, not as transparent as hydrogen, but this image doesn't correspond to the methanol. Methanol, it produces a very tiny flame, almost not visible. So this spectrum is very characteristic of the emission by only CO2 and H2O. Just to go further, what I can show you is some images obtained by the hyperspectral camera. Let's start with that one. Okay, so in this figure, we find again this whole interferogram that contains all the fluctuation due to the fact that the flame is not static. Okay, it is turbulent. So you can move, just to show you the interferograms at different points of the image. Okay. After the correction, we obtain this kind of interferogram here. So now we have a constant baseline. Okay, and the interferogram is cleaner. So same, we can change the position in the image to see what are the different interferograms that have been acquired by the instrument. And after the Fourier transform, what we obtain is the spectrum here. Why is it? Yeah, so this is the spectrum of the methanol flame. We find again this peak here, which is due to the CO2 on this part here that corresponds to the emission by the water vapor. Once again, you can see the spectrum at different position in the flame. Okay, and what is interesting is if we see what's happening near the surface of the pool fire. So maybe you cannot see it very clearly, but here there is a small bump. Maybe I can make a close-up. Okay, so if you go, sorry, up. Okay, when you go near the surface, the signal at this wavelength is larger. Okay, what can be done also is instead of changing the position of the observation point, you can change the wavelength. That is here, what you see is the image at this wave number that corresponds to the emission by the carbon dioxide. But if you go here, that corresponds to the emission by the fuel vapor, that is the methanol vapor. you can see that the image is very different. That is, this emission here at this wavelength occur just above the pool fire. Okay, there is almost no signal in the upper part of the flame. Last thing I wanted to show you is the result obtained by a kerosene flame. Here, I have to find it. Okay, so this is the spectrum of diesel. So maybe for you it seems the same, but if you look carefully to the spectrum, you can see that there is a continuous spectrum between the emission band due to the gas. Okay, that is, if you compare here, the signal is not null. Okay, maybe I can zoom more. Okay, if you consider the methanol flame, or if you consider the hydrogen flame or the methane flame, there is no signal at all here because the combustion gases cannot emit in this part. Okay, it can emit here CO2, in this part H2O. Okay, but all this radiation in this part, and so on, is just due to the soot which is contained in the flame. So, as a conclusion, we have used the hyperspectral camera by Telops to measure the emission spectrum of H2, H2CH4 on pure CH4 flames. And we have obtained some very good quality spectra with a 0.25 centimeter minus 1 spectral resolution. We have used the L distribution approach to model this spectra, and using a SPSO inversion, we got some flame temperature on species molar fraction. Regarding diffusion turbulent flame, this is an ongoing work. And what is maybe encouraging is that the correction of the interferogram leads to spectra that are meaningful. That is, the result makes sense, but it needs an exploration of what we can do with these spectra to obtain some quantitative information. Regarding the perspective, we wanted to explore some other inversion method, example given the Bayesian inference, and also to optimize the choice of restricted wavelength range, because for now, as I explained you, we perform the inversion on the full ranges, and it is not necessary because it's used a lot of computation time. And yes, concerning the diffusion turbulent flame, as I said, we have to evaluate the effect of the fluctuations of the interferogram on the spectra, and to model and inverse these spectra. Thank you for listening.
Thank you very much, Gilles. It is very interesting. I'm sure people have well, I saw a couple of questions coming in. But first, yeah, let me just thank you very much for going through this presentation. Like I said at the beginning, it is recorded, so there's a lot of information to unpack here. So you presented it very well. There's a lot of information to unpack, so hopefully people will have the chance to listen to it some more, because yeah, you brushed over very quickly the fact that you handled the scene change artifacts of the interferogram, you know, but there's a lot of work to handle artifacts, and there's a lot of mathematics involved. So I know it's a lot of work, so I appreciate it. We don't have a lot of time, unfortunately. I want to keep this under an hour, so maybe we'll have maybe we can address the two questions that came in right away. So if you want, I'll read it to you. So question from Pedro Coelho. I'm sure I don't pronounce it very good, but sorry. But how accurate is the assumption of uniform chemical composition in the hot layer? So I saw that also, that you mentioned that the temperature in your hydrogen flame, the temperature distribution was very uniform. The gas concentration wasn't very uniform. So is this kind of expected, or is this a?
To be honest, I don't know really. It's what we obtained. I don't have any idea about this how good the results are, because we don't have any other comparison between the results we just obtained on other techniques.
Yeah, Pedro has another question, but we won't be able to answer it right now. So how is the interferogram correction carried out in case of turbulent flames? I guess that is pretty complex.
Yes, the idea is just to low filtering the signal, because the useful information, that is the interferogram, it has a high frequency. All the information is at very high frequency, and if you compare the fluctuations are at low frequency. So what you can do is just to low filtering the signal. So what you obtain is just the signal without the interferogram, and after you can divide the total signal by the low pass filtering signal in order to correct the baseline. So it is the main idea, and this was described in some publication elsewhere.
All right, so it's an hour already. I think we'll end the webinar here. I know some questions, some additional questions came in. So like I said, everything is recorded. We have your questions, and we'll take some time offline to answer them and relay the answers to all of you, along with a link to the recording of this webinar. So we'll be in touch, is what I'm trying to say. So don't worry, your questions will be answered. So again, I would like to thank our presenter, Gilles Parent, here today for this amazing presentation. So thank you.
Welcome.
And thank you to all of you to join us on this webinar, and hopefully we'll see you next time on another Telops webinar. So on that note, thank you again, and I wish you all to have a really nice day. See you next time.